Good class. So today we are starting another physics UTME class on gas laws. So today we are continuing where we stopped in the last class. So in the last class we did gas laws where we did oil law and track law, and then we did some working examples. So today we'll continue from where we stopped in the last class. If you missed the last class, do well to go to TPATHS channel on YouTube, and then you can watch these videos and the tutorials. All right. So gas laws. So today we'll be working with pressure law. We'll start from where we start. Pressure law. So what's pressure law? Pressure law, sometimes it's called Gay-Lussac's law. It states that the pressure of a gas is directly proportional to the absolute temperature provided that the volume of the gas is constant. All right. So what it means is simply the pressure of a gas, sometimes called pressure law, Gay-Lussac's law. So it means the pressure of the gas is directly proportional to the absolute temperature. That's absolute temperature in Kelvin, provided that the volume is constant. So working with this, I can say P, which is my pressure, is equal to KT. And this K here is my proportionality constant. So this K here is the proportionality constant. So to get the value of K, I can see my P, or I can say, sorry, K is equals to P over T. That's dividing through by T. I have K is equals to P over T. Here this is my constant. And I said in the last class that this guy will remain a constant as far as this values doesn't change. So now if I increase the pressure and I also increase the temperature, this K is always going to remain a constant, which means I can say K is equal to P1 over T1, and I can say K is equal to P2 over T2, like that. So which means I can say P1 over T1 is equal to P2 over T2. So right, once again, what's pressure law? Okay, Lussac's law. Pressure law is simply, it simply states that the pressure of a gas is directly proportional to its absolute temperature, provided that the volume is held at constant. So that's pressure law. Sometimes they call it the Lussac's law. So this is the formula we use for pressure law. This P1 over T1 is equals to P2 over T2. Don't forget, we are working with gases, all our temperature, our absolute temperature, that is, they are measured in Kelvin, the units are Kelvin. So when you have in your question, it is given in Celsius, you try and convert it to Kelvin by adding 273. All right, so that's pressure law. So now let's take example of pressure law. All right, so let's take an example. Okay, so the first example says the tire pressure of a car was found to be 150 centimeter mercury in the morning at a temperature of 27 degrees Celsius. So now, don't forget in the last class I said when we're using pressure, we're working with centimeter mercury. So the unit of pressure is either centimeter mercury, millimeter mercury, ATM, or Newton per meter square. So these four guys are all units of pressure. So when you see millimeter mercury, centimeter mercury, ATM, which is atmosphere, or Newton per meter square, you know they are talking about pressure. So now in this question, the question says the tire pressure of a car was found to be 150 centimeter mercury. 150 centimeter of mercury. All right, so I'll just write this down. Pressure, that's P1, is 150 centimeter of mercury in the morning at a temperature of 27 degrees Celsius. So at 150 centimeter mercury, the temperature is 27 degrees Celsius. All right, so now hard driving in the afternoon raised the temperature of the tire to 57 degrees Celsius. So now in the afternoon, in the morning, the temperature was 27 degrees Celsius. So after driving, the temperature of the car tire was increased to 57 degrees Celsius, which is my T2. I say 57 degrees Celsius. All right, so now the tire pressure in the afternoon. Now, what I want to calculate is the tire pressure at this particular temperature, at a temperature of 57 degrees Celsius. All right, so now the question says at 27 degrees Celsius, the pressure of the car is 150 centimeter of mercury. Now, at 57 degrees Celsius, how do I calculate the pressure? So I can say P2 is equal to the unknown, which I don't know. So now, yeah, I have my formula here. P1 over T1 is equal to P2 over T2. All right. So what I'll do is I'll just use the parameters I have here in the question into this formula. So first one is P1, which is 150 centimeter mercury, 150 divided by my T1. Now I said when you're working with temperature, you make sure to convert all your temperature to absolute temperature, which is in Kelvin. So the first thing I have to do here is I want to convert these two temperatures to Kelvin. So my T1 will become 27 plus 273, right? So converting it to Kelvin. So if I add 27 to 273, I'm definitely going to have 300. So 300 Kelvin. So now this is absolute temperature. Also, I have my T2, which is 57 degrees. 57 degrees. I'm also converting it to Kelvin from Celsius. So what am I going to do? I'm also going to add 273. That's plus 273. All right. So now 57 plus 273, that's going to give me 330. 330 Kelvin. I hope you guys are following me. So I have this. Now, this my two temperature are already at absolute temperature. That's they're in Kelvin as the unit. So now my T1 is now 300 is equal to my P2, which is the unknown value, what I'm looking for, over my T2. My T2 is 330 Kelvin. So this will be 330. So now from here, I can say 151, 152. That's 150 can go in 300 twice. So this is 1 over 2. And from here, I can cross multiply. 2 times P2 will give me 2 P2 is equal to 330 times 1 will give me 330. Now here, to find the value of my P2, I'm simply going to divide through by 2. I divide by 2. I'm going to have P2 is equal to 165. Now I'm going to add my unit, the unit of pressure, which is centimeter mercury. All right, so now the question says the tire pressure in the afternoon as A increased by 15 centimeter mercury, B decreased by 15 centimeter mercury, C increased by 25.5 centimeter mercury, and D decreased by 22.50 centimeter of mercury. So now we'll check the options one after the other. I'll start from option D. Option D says decreased by 22.50 centimeter mercury. No, so now in the morning, my pressure was 150 centimeter of mercury. Now in the afternoon, it is now 165 centimeter of mercury. As you can see, the temperature has increased by 15 centimeter mercury. How do I know? I'm simply subtracting 165 from 150, and this is giving me 15 centimeter of mercury. That's 165, which is the pressure of the tire in the afternoon, subtracted from 150 centimeter of mercury, which is the pressure of the tire in the morning, gave me 15 centimeter of mercury. So which means the tire pressure in the afternoon has increased by 15.0 centimeter mercury, which is option A. All right, so option A is my answer because it increased from 150 centimeter mercury to 165 centimeter mercury. Option A is my answer. So now what I did was I wrote down the parameters in the question, made sure I'm converting my degrees Celsius to absolute temperature, which is in Kelvin, by adding 273, like just what I did here. I added 273 to 27 to get 300. And here also I added 273 to 57 to get 330. Then I imputed everything into my formula here, which is P1 is equals to P1 over T1 is equal to P2 over T2. All right. So let's move to another example. Example 2 says, if the volume of a gas increases steadily as the temperature increases at constant temperature, the gas obeys A. Graham's law, B. Boyle's law, C. Pressure law, D. Charles' law. So now the question says, the volume of a gas increases steadily as the temperature increases at constant pressure. The gas obeys. So what it is trying to say is, when the volume is increasing, the temperature is also increasing, which I can say B is directly proportional to C. So now if a variable is increasing, and then, okay, let me say there are two variables, and when one of the variable increases, and then the other also increases, it means they are directly proportional to themselves. Okay, I'll go over it again. Let's say we have two variables, right? And then when one of the variable increases and the other increases, it means those two variables are proportional to themselves. Just like I say, I have this phone here and this marker here. All right, so if this marker increases, and also the increase in this marker leads to an increase in the size of this phone, it means these two guys, they are proportional to themselves. But then if an increase in this leads to a decrease in the size of this spoon, then they are inversely proportional. All right. So now, going back to our question, says if the volume of a gas increases steadily as the temperature increases at constant pressure, the gas obeys. So what I can see here is my pressure is constant, and then V is directly proportional to T. So the gas that obeys this law is Charles' law. This gas obeys Charles' law because Charles' law says the volume of a fixed mass of gas is directly proportional to its absolute temperature, provided that the pressure is constant. So which means that particular gas obeys Charles' law. I think I'm clear. So this is Charles' law, which is option D. It's my answer because Charles' law is the volume of a fixed mass of gas directly proportional to the absolute temperature. So that is option D. All right. So now we're moving to ideal gas equation. Ideal gas equation. So ideal gas equation simply occurs when the volume, the pressure, and then the temperature of a gas are varying. That is, they all vary, they change in values. So any of the two laws between Charles' law, Boyle's law, and pressure law can be used to get my ideal gas equation. So now let's start from here. I'm going to write out the three laws. So now, this is Boyle's law. This is Charles' law. Why this is pressure law or Gibbs-Sachs law? Pressure law or Gibbs-Sachs law. All right, so I have these three laws. So now if I'm combining any of these three laws together and any two of these three laws together, I should be getting ideal gas equation. So now how do I do this? So firstly, I want to combine my Boyle's law and Charles' law. So combining Boyle's law and Charles' law, I can say P is inversely proportional to P, and then at the same time, it is directly proportional to T. So saying this, I'm saying volume is inversely proportional to P. This is this, and directly proportional to T, just like this. So I can say V is becomes this. All right, joint variation. So this is what I have. V is inversely proportional to P and directly proportional to T. So I can say here that V is proportional to T over P. And then from here, I can go over. I hope you guys are following me. So what I want to do is I want to derive my ideal gas equation. In instances where we use them, is when the pressure, the volume, and the temperature of a gas all vary. So now here I have B is proportional to T over P, and I can say B is equal to K T over P, where this K is my proportionality constant. So now if I cross multiply, I have PV is equal to KT, and then I can say K is equal to PV over T. So now using the same thing I used for Boyle's law, Charles' law, and pressure law, I can say P1 over T1 is equal to P2 V2 over T2. So now this is ideal gas equation. How do I get it? I got it by combining Boyle's law and Charles' law. So when I combine Boyle's law and Charles' law, combining them, I got this P1 V1 equals to P2 V2. Using joint variation, that is, the volume is inversely proportional to pressure and then directly proportional to temperature, which is Boyle's law and Charles' law, combination of Boyle's law and Charles' law. So now I came here and used joint variation to get P is proportional to T over P. And then coming here, I said, using my proportionality constant K, I said V is equals to KT over P. And then here I say PV by cross multiplying, I brought this P to this side. PV is equal to KT. And then K becomes, which is my proportionality constant, becomes PV over T by dividing through by T. All right. So I can say P1 V1 over T1 is equal to P2 V2 over T2. P is my pressure, volume, and temperature. Don't forget absolute temperature in Kelvin, rather, in Kelvin. All right, so I can also combine these two equations together. I can combine these two equations together to get this. So I can say T is directly proportional to V, and at the same time, it is directly proportional to P. That's combining Charles' law and pressure law. So if I'm combining Charles' law and pressure law, I say T is directly proportional to V, and at the same time, directly proportional to P. That's T is directly proportional to P and directly proportional to V. So now here I can have joint variation. T is directly proportional to P times V. And I can say T is directly proportional to V All right, so from here, I can say PV is directly proportional to T, just like this. And then here I will say PV is equal to KT, where this K is my proportionality constant. All right, so now to get the value of my K, I can divide through by T, and I say K is equal to PV over T. So if I did the same thing just like I did here, I also have P1 V1 over T1 is equal to P2 V2 over T2. All right, that's by combining Charles' law and pressure law. I can also go ahead and combine Boyle's law and pressure law. I also get the same thing. All right, so you guys can do that by yourself. I've done this too. But just add it at the back of your mind that this is ideal gas equation. But then you can try it just because of time. I won't do that last one. You can try combining pressure law and Boyle's law, and then you see you also have this equation here, which is P1 V1 over T1 is equal to P2 V2 over T2. All right, let's take an example quick. Okay, all right. The example says 200 centimeter cube of a gas is collected at 27 degrees Celsius and 70 millimeter mercury and 70 millimeter of 700 millimeter of mercury. All right, I think there's a mistake. The question is 2000 centimeter cube of a gas is collected at 27 degrees Celsius and 700 millimeter mercury. What is the volume of the gas at standard temperature and pressure? All right, so I want to write out the parameters in my questions first. It says 2000 centimeter cube of a gas. 2000 centimeter cube, that's volume. So my volume, which is V1, 2000 centimeter cube. All right. And then it's collected at 27 degrees Celsius. 27 degrees Celsius is my temperature, which is T1. 27 degrees Celsius. And 700 millimeter mercury, which is P1, which is my pressure, 700 millimeter of mercury. All right. So now I have this. It now says, what is the volume of the gas at standard temperature and pressure? So now what is standard temperature and pressure? The standard temperature of a gas is 273 Kelvin. While the standard pressure of a gas is 760 millimeter mercury. Okay, let me write this down. Standard pressure, which is SP of a gas, is equal to 760 millimeter mercury. Have it at the back of your mind. This is 760 millimeter mercury. While standard temperature of a gas is 273 Kelvin. All right. So now the question now says, what is the volume of the gas at standard temperature and pressure? So which means my pressure is 760 millimeter mercury and the temperature is 273 Kelvin. So my P2 here is going to be 760 millimeter of mercury, while my T2 is going to be 273 Kelvin, which is the standard temperature of all gases. 273 Kelvin. All right. So now what I want to find is the volume of that particular gas at the standard pressure of that gas and the standard temperature of that gas. So V2 is my unknown. All right. So going ahead, using the ideal gas equation that we just derived here, which is P1 V1 over T1 is equal to P2 V2 over T2. So this is the formula we'll be using because here the volume is varying, the pressure is varying, and the temperature is also varying. So we're going to use ideal gas equation. All right, so now I'm going to take it one by one. My P1 is 700 times my V1, 2000, divided by my T1. Now, the first thing I have to do is I want to convert this to Kelvin, which is absolute temperature. So now converting this to Kelvin, I'm going to add 273 to it to convert it to Kelvin. So this will be plus 273. Convert it to absolute temperature. So 27 plus 273 is going to give me 300 Kelvin. So my T1 is going to be 300 Kelvin. So I'm going to write here T1 300 equal to my P2, which is 760 times V2, which is the unknown that I'm looking for, P2, divided by T2, which is 273. Don't forget, I got this T2 by getting the standard pressure and temperature. My T2 and P2, the standard pressure and temperature of all gases. Have it at the back of your mind. Standard pressure of all gases is 760 millimeter mercury, while the standard temperature of all gases is 273 Kelvin. All right, so here I can work this out. I can say this one cancels out this and this cancels out this. And then I can say 7 times 2000 divided by 3 is equal to 760 times V2 over 273. So from here, I can cross multiply. That is, I multiply this with this and then multiply this with this. So I'll have 7 times 2000 times 273, that's times this, is equal to this. We'll multiply this here. 3 times 760 times V2. All right, so let's do the arithmetic. So now that will be 7 times 2000 times 273. Okay, that's going to give me 3822000 is equal to, so 3 times 360, sorry, rather 760, 2280 times V2. So now to get the value of my V2 here, I need to divide through by 2280. All right, so I'll divide this by 2280. That's to get the value of my V2, which is the volume. And I'm also dividing this by 2280. All right, so I'm going to continue this from here. Don't forget, we are still using ideal gas equation, which is this equation I circled here. Don't forget. So now I have 3822000 divided by 2280 equal to 2280 times V2 divided by 2280. So definitely this is going to cancel out this. So now what I want to get is this divided by this. That's 3822000 divided by 2280. All right. So this gave me V2 is equal to 1676.3 centimeter cube. So now what I have to do is, here is the value of my volume at standard pressure and temperature of the gas, 1676.3 centimeter cube. So now, which is option C? The answer that correlates, I mean, the answer that correlates with the option here is, or the option that correlates with my answer here is option C, which is 1676.3 centimeter cube is the volume of the gas at standard temperature and pressure. Option C. All right. So now we're moving to general gas law. But before we move to general gas law, let me quickly do a review of this question. First thing is, I wrote down all the parameters in the question. I converted my temperatures to Kelvin scale, which is absolute temperature. And then don't forget, I said the absolute, the standard pressure of a gas is 760 millimeter of mercury, while the standard temperature of a gas is 273 Kelvin. All right, so having that, I imputed all of those things into this formula here, into this equation, which is P1 V1 over T1 is equal to P2 V2 over T2. And then I worked everything out to get 1676.3 centimeter cube. All right, so now let's move to general gas law. So general gas law states that the product of pressure and volume of a gas, the product of the pressure and volume of the gas is directly proportional to the number of moles of the gas at absolute temperature. All right, the product of the pressure and volume is directly proportional to the number of moles of the gas and the temperature and the absolute temperature. All right, so what this means is the product of pressure and volume, this is this. Product means multiplication, that's product of pressure and volume is directly proportional to the number of moles, to represent number of moles N, and the absolute temperature of the gas. So now this is what general gas law says. The pressure of a mass of gas and the volume of the gas is directly proportional to the number of moles and the absolute temperature. So I can say here PV is directly proportional to NT. And here I can say PV is equal to KNT. But now here in general gas law, our K, which is our proportionality constant, is not as K, it is written as R, which is our own gas proportionality constant, which is 8.3 joule per Kelvin per mole. All right. So I'm going to write this. Instead of having this K here, I'm going to have R. So my PV is going to be equals to nRT. So now this R here is the proportionality constant of this general gas law, which is the gas proportionality constant, which is equal to 8.3 joule per mole per Kelvin. All right. So my R is a constant, which is always equal to 8.3 joule per mole per Kelvin. So you have that at the back of your mind that this value R here is equal to 8.3. Okay, let me write it here. R is equal to 8.3 joule per mole per Kelvin. All right, so this is the value of my R, which is the constant. So you have this at the back of your mind. In any question, probably might not be given the value of this R. You know that your R is 8.3 joule per mole per Kelvin. Why this N here is the number of moles of the gas. Number of moles can be 1 mole, 2 moles of the gas, 6 moles, 1.5 moles. So N is number of moles. T is the absolute temperature. Why my V here is the volume of the gas, and P is the pressure of the gas. So general gas law simply states that the product of the volume and the pressure is directly proportional to the number of moles and the temperature of that gas. All right. So now here we'll be working with an example. So here is the equation we have. So after simplifying all of this, I have PV is equal to nRT, the pressure of the gas, the volume of the gas. N is the number of moles. R is the constant, which I wrote up here, 8.3 joule per mole per Kelvin. And then T is the absolute temperature. All right. So I'll be taking an example. Taking an example. All these examples I'm taking, they are from past questions. So when you practice your past questions, you are definitely going to see all these examples here. So when we are working all of this out, I hope you guys pay utmost attention to what we are working out here, and then you should also practice on your own. All right. So the question says, calculate the temperature of 6 moles of an ideal gas at a pressure of 7.6 times 10 raised to the power of 6 Newton per meter squared. All right. So calculate the temperature of 6 moles of the gas. Temperature is what you're asking us to find. That's the first thing. That's the unknown variable. Of 6 moles, I said N is number of moles. So which means my N is 6 moles. All right. Of an ideal gas at a pressure of 7.6 times 10 raised to the power of 6. So the pressure is 7.6 times 10 raised to the power of 6 Newton per meter square. Don't forget, and I in the earlier on, I gave you 4 units of pressure, which is ATM, which is atmosphere, centimeter of mercury, millimeter of mercury, and then Newton per meter square. All right. With a volume of 10 raised to the power of minus 3 meter cube. So the volume is 10 raised to the power of minus 3 meter cube. And then the question says R is equal to 8.3 joule per mole per Kelvin. So R is 8.3 joule per mole per Kelvin, which I've already written down here. All right. So this is it. This is the constant. It's always 8.3 joule per mole per Kelvin. So now what I want to calculate here is my temperature. So using this formula, PV is equal to nRT. What I'm going to do is I'm going to replace all these parameters here in my formula. I'm going to input all these parameters here in my formula. So now my P is pressure, which is 7.6 times 10 to the power of 6. This will be 7.6 times 10 to the power of 6. That's my P multiplied by 10 raised to the power of minus 3, which is the volume, 10 raised to the power of minus 3. It's equal to my N is my number of moles, which is 6. 6 multiplied by 8.3, which is R, times T, which is the unknown that I'm looking for. All right, so here I'm going to evaluate this. So here I can just use indices to divide this, and I can say 7.6. When I multiply this, I'll say 7.6 times 10 to the power of 3. You don't know why I got this. If you remember indices when you did mathematics in secondary school, when you have numbers of the same base, when you have the same base, and then you can just, when you're multiplying, you add the powers. When you're dividing, you subtract. So since this is multiplication, I just add the powers. That's 6 plus minus 3. And then plus times minus is minus, right? So I can see 10 raised to the power of 6 minus 3, and 6 minus 3 gave me 3. So this is how I got this raised to the power of 3 here. So I can say 7.6 times 10 raised to the power of 3 is equal to 6 times 8.3 times T. So from here, I'll just say 7.6 times 10 raised to the power of 3 is equal to, so I want to multiply 8.3 times 6. What is it going to give me? 8.3 times 6. So that's going to give me 49.8. 49.8 times T. So from here, to get the value of my T, which is the absolute temperature, I can divide through by 49.8. And I divide this also by 49.8. And here, when I divide by 49.8, I have my T to be equal to 152.6 Kelvin. All right, because I'm calculating temperature. the value of my temperature is 152.6 Kelvin. But yeah, according to our options here, the options are given in whole numbers. So what I'm going to do is I'm going to convert this my answer here to whole number. So I'll say T is equal to 153 Kelvin. That's converting this to a whole number. This is a number greater than 5, so I can approximate it. It becomes 153 Kelvin. So now I'm checking the option that correlates with my answer, option C. So the answer to this guy here is 153 Kelvin, and that is option C. So now we'll take another example. All right, real quick. The example says the pressure of 1 mole of an ideal gas. I'm going to work that out here. The pressure of 1 mole of an ideal gas of volume 10 raised to the power of minus 2 meter cube at the temperature of 27 degrees Celsius is. So what I'm to find is pressure. I'm to calculate the pressure. That is my unknown here. And then the mole is, number of mole is 1 mole. Then R is always equal to 8.3 joule per mole per Kelvin. All right. So now, the next thing is my temperature is 27 degrees Celsius, which I have to convert to Kelvin scale. Converting to Kelvin scale, I'm adding 273 to it to convert to Kelvin scale. So from adding this, I'll have 300 Kelvin. All right. And then the volume is 10 raised to the power of minus 2 meter cube. So this is the volume, my temperature, my constant, the number of moles, and P. I'm calculating for P, which is pressure. So I can say PV is equal to nRT, which is my formula, ideal gas equation. Sorry, general gas equation. And then my P times 10 raised to the power minus 2 is equal to, my N is 1, so I can say 1 times 8.3 times my T is 300. All right. So now I will multiply all of this together by saying 8.3 times 1 times 300, which is giving me 2,490. 2,490. So I can say P is equal P times 10 raised to the power minus 2 is equal to 2,490. So for me to get the value of my P, I'm simply going to divide by 10 raised to the power minus 2, and dividing this by 10 raised to the power minus 2. All right. So dividing this, I'll have my P equal to 249,000 Newton per meter square. All right. So the question was given in standard form. So I can convert this to standard form by saying bringing the points from here to the first digit here. So I can say 1, 2, 3, 4, 5. And because I'm moving from right to left, my the power is going to be a positive number. So this is going to be 2.49 times 10 raised to the power of 5 because I moved the points 5 times. That's 1, 2, 3, 4, 5. This will be raised to the power of 5 Newton meter squared. Why it is not a negative number is because it is moving from right to left. If I'm moving it from left to right, it's going to be a negative number. So my answer here is 2.49 times 10 raised to the power of 5 Newton per meter squared, which is option C. So yeah. All right. So we're going to move to, okay, let me just go over this. I think our time is almost up. And then let me just go over it. And then next class, we'll move to another topic, which is pressure. All right. So now, the first thing I did is I wrote down, okay, this is the first question and this is the second question. So what I did is in both questions, I'm just going to fill out the parameters in the question. I'm going to write it out just like I did here and I did here. And then I'm going to use it in this formula. That's I'm going to impute all the parameters I have here into the formula here, which is PV is equals to nRT. So imputing it, I'll just evaluate, and after evaluating, I get value. So I can be asked to look for T, which is temperature, just like here. I can also be asked to look for volume. I can be asked to look for the pressure, which is what I did here. And sometimes you can be asked to look for number of moles. So what you can just do is after this class, you can go over to your past questions and then start opening pages and start working on what we've been discussing so far since when we started these lessons on gas laws. So in the next class, we'll be moving to pressure. So I hope you guys don't lag behind because when we are working with pressure, we'll be using all these values in pressure, Newton meter square, and all of that. So we'll meet in the next class. Goodbye.